Next, I'll be teaching you some rules to specify the configuration of a chiral center. Now basically, right, you need to know the ranking. Remember last time in alkenes we talked about the E and the Z form. It is the same. The Cahn-Ingold-Prelog rule, the CIP rule. I hope you can still remember them. So what happens is now we are using this rule for a sp3 carbon center and determine its configuration. Take note, not conformation but configuration. We are going via the atomic mass. So first of all, we assign the priorities on the 4 groups of a chiral carbon, and we orientate the molecules so that the group of the lowest priority, which we call number 4, points to the back of you. I mean, for me it's to the back, so closer to you, but for you is towards me. And then we look at the 3 remaining substituents. For the R configuration, from the highest to the lowest priority, if you do a rotation, if it is clockwise, it's R. If it's counterclockwise, then it's S. So basically, you see this molecule here. Okay, suppose we know that H, the white ball, is the lowest priority. So I send it back. I'm using from your perspective, so you push it to the back of you. Black is a carbon. And you see that this is orange, red, and green. Suppose we go by alphabetical order. Suppose this is number 1, 2, and 3. So what do you see? 1, 2, 3 is going counterclockwise, right? So this molecule here to you is S. To me, it's still S because when I do this from here, I'm going counterclockwise. So it's always S. But if it's the other way around, clockwise, then this molecule is R. Now for lactic acid, let's take a look. For this molecule here, H is always number 4 because it's the lowest priority. Carbon, carbon. So this is the highest priority, number 1. This is number 2, and this is number 3. Using this, we know that COH is a higher priority than methyl group. So now we push the H to the back like this, and we see that rotation from 1 to 2 to 3 is clockwise, and that's why it's R. And then for the enantiomeric form, this is number 4, this is number 1, 2, and 3. You see that it is S because it's going counterclockwise. This molecule, please give yourself a try. This is actually S because when you drive the wheel, right, you see that 1, 2, 3 goes counterclockwise. And for the bottom case, this molecule here, do some practice. This is again S because when you rotate the 1, 2, 3, you still get counterclockwise. This example I'm trying to show you here is to illustrate that even though you have S in both cases, but you see this is S negative glyceraldehyde. The bottom is S positive alanine. So plus and minus have no link with S and R. Totally no relationship at all. Which means that I could have a plus, S minus, R plus, and R minus. No relationship at all. This is again another kind of a diagram to help you to see, push your number 4 to the back, and then you do the rotation, and then you do the rotation and see 1, 2, 3 goes which way. Is it clockwise or counterclockwise? That'd be easier. Now in class, maybe I can demonstrate to you in a much better way because we have the connection there, a physical interaction, so you can learn better. But for now, if you can try and you do a few exercises and then you check answer, you got it right, that means you're all good. So this example here shows an R2-chlorobutane. I hope you use this method and get this right. That'd be perfect. Now what about molecules that have more than 1 chiral centers? Because we know that compounds are big. They contain so many carbons, and it is not uncommon to have more than 1 chiral centers. So the number of enantiomers that it has, there is a formula. It can have up to 2 power n. Take note, it can have up to 2. It doesn't mean that it must have 2 power n. Okay? For amino acids like threonine, there are 2 chiral centers, one on the carbon 2, one on the carbon 3. So 2 power 2 is 4. So we could have 4 possible stereoisomers. These are the 4. At the second carbon, it is a R configuration, third carbon R configuration, so it's RR. This is SS, RS, SR. These two are enantiomers because when you reflect an R, you get the S. When you reflect the S, you get the R at the same position. These two are enantiomers because R reflect give you S, R reflect give you S. So you see, these are mirror images. I just went through this with you. Now something called the diastereomers. They are stereoisomers that are not mirror images. Back to that example we talked about the previous slide. If we pick this and that, they are somewhat related, but what is the term to describe them? They are called diastereomer. Because now you have two chiral centers within the same molecule, but then now you only change one of them. So they are non-superimposable to each other, but they are not exactly enantiomers, and they are also not mirror images. So we call them diastereomer. I hope this shows you the true picture that you can understand. R and S flip, S and R flip, so these are enantiomer. R become S, R become S, so these two are enantiomer. But if you compare these, they're diastereomer. When you compare these, they're diastereomer. Alright. Epimers, another term here. It just tells you that there are two diastereomers that differ only at one chiral center, and all the rest are the same. So for these two, cholestanol and coprostanol, they are epimers because all the chiral centers are the same configuration except for one of them, carbon 5. For tartaric acid, you notice that it is a very funny molecule because it has two chiral centers, and when we draw this out in this manner, we have 2R, 3R, and 2S, 3S. And then when we do the other one, we have 2R, 3S, and 2S, 3R. But the thing is, for this molecule, we see a plane of symmetry. And recall that when a molecule has a plane of symmetry, it is not chiral. So what does that tell you? It tells you that these two are actually identical. They are the same. They are enantiomers, mirror images of each other. It means that, all in all, tartaric acid only has 3 different stereoisomers because these two are identical. So we call them meso compounds. Meso compounds is what meso compounds. So meso compounds are compounds that contains chiral centers but still contains a plane of symmetry. So it means the overall conclusion is a compound can contain chiral centers but it could be overall achiral. Not surprising. For threonine, you have 2 chiral centers, 2 pairs of enantiomers, and a total of 4 stereoisomers because there's no kind of overlapping here. For tartaric acid, 2 chiral centers, a pair of enantiomer, and 1 meso compound, so in total you have 3 stereoisomers. For the plus and the minus tartaric acid, we know that they are enantiomers of each other. They have the same identical physical property like melting point, boiling point, and density. We went through this again, but let's drill it into you. And they differ in the sign of the rotation of the plane, polarized light. For the meso tartaric acid form, there's no mirror image relationship. So it's a different compound, and hence they have different physical property. So see that, right? The specific rotation is 0 because it is not even chiral. Melting point different from these two, different density, different solubility.